Hello everybody! In this video we're going to finish off our section on continuous functions by stating and proving what we'll call here a topological characterization of continuous functions. So we'll get to the theorem and you'll see what I mean by that. So the theorem, which I'll summarize here, is saying that continuous preimages, okay, already that sounds complicated, of open sets are open. All right, so let's make this more explicit. So let's say I have a function f from a domain D, but I'm going to assume here that D is an open set. All right? And let's say we know that f, actually we want to talk about whether f is continuous. So let's start it here. F is continuous if and only if the f preimage. Okay, so before I even go any further, let's talk about what I mean by that. So if I have my function f, okay, it's going from D to R. The preimage, if I just had some point, the preimage of f would be all of the points of D that map to this one given point. Okay, so if that was some x, then these 3 points on the left would be what we called the preimage of the point x. And so that'd be all 3 of these. It's a set, okay? Now, if instead of an x, I actually have a subset of R, so maybe I take some, maybe some interval here, all right? We'll call that D. No, maybe not D. How about O? So say I have some subset O, I could ask what are all the points in D that map into this yellow bar O, okay? And so maybe that ends up being something like this. Right? And you say, okay, that's all the stuff that maps into there. Okay, and so then this green bar would be the preimage of the subset O. So when I talk about an F preimage, that's what I'm talking about. All the elements in D that map to whatever given set we're talking about. So the statement here is that F is continuous if and only if the F preimage of every open set, right, or open subset, if you like, of R is an open set. Okay, so we're talking about these preimage sets here. We want these to always be open if we start with an open set in the codomain. All right, so we're going to try to prove this. All right, so let's start. And we'll start by proving that if F is continuous, then every F preimage of an open set is open. So if F is continuous, okay, and well, let's see. We're going to want to take some open subset of R. So we'll have some open subset, we'll call it O of R. And we want to show that the preimage is open. Okay, so recall that for a set to be open, we need to look at every point, say in that set, and we could show that it is an interior point. And in the homework, one of the reformulations we gave is that if I take some point and I want to show that it's an interior point, I just need to show that it's contained in some open set, right, or some open subset. So let me choose some point in the preimage of O. Okay, so and let, and A, little a will be some element in the preimage of O. All right, so we want to show, okay, that the preimage of O contains an open A set. Okay, so remember that means it's just some open set that contains A. Okay, fine. So we have all these assumptions now, and, well, what do we know? Well, if A is in the preimage of O, that means when you apply F to A, you end up in O. So we can just record that. F of A is an element of O. All right, and now we're in O, and we know something about O. O, there it is. O is open. And since O is open, since O is open, we know that it contains some f of a coin. Okay, so there exists an f of a coin. Okay, maybe it'll be something like f of a minus epsilon, f of a plus epsilon, right, contained in O. All right, so here epsilon, right, is some positive real number. Okay, but we also know that f is continuous. And since f is continuous, then there's going to be some a coin that is going to map into this f of a coin. All right, so since f is continuous, there exists an a coin, and let's call it a minus, I don't know, delta of epsilon, because it depends on epsilon, a plus delta of epsilon, such that if I apply f to anything in this interval, a minus delta of epsilon, a plus delta of epsilon, you end up in this f of a coin. Okay, that's what continuity brings to the table. Okay, and of course this is still a subset of O. Fine. Now, what I should say here is, of course, this is not quite 100% accurate, right? Because F has domain D. And so when I, looks like we have one extra parenthesis there. When I apply F to, one fewer parenthesis. When I apply F to this interval, there may be points in this interval that aren't in the domain, right? They're not in D. So what we actually have to do is, well, we use this notation here. Sub D just means intersect with D. Okay, so recall here that this is equal to a minus delta of epsilon, a plus delta of epsilon, intersected with D. Okay, so that's part of that thing we got to do, right? Whenever we evaluate a function, we got to make sure the points are in the domain. Fine. However, this A coin is open, right? It's an A coin, centered open interval. Okay, but this D by assumption is also open. And we know that the intersection of any two open sets is open. So this intersection is open. So what I've done is I have found an open set that contains A, right? A is sitting right down in the middle of this thing. And F applied to that A ends up in O. Right? But what does that mean? That means that this set, which is in the preimage of O, okay? So this A minus delta of epsilon, A plus delta of epsilon, intersected with D, right? When I apply F to it, I end up in O. So this is contained in the preimage of O. And A is an element of this set, and it is an open set. And so this implies that the preimage of O contains an open A set. And, well, you look up above. That's exactly what we were trying to prove. Okay, this shows now, since this was for any A in the preimage of O, this implies that the preimage of O is open. Okay, so this proves if you have a continuous function, then the F preimage of every open subset is an open set. All right, now let's go the other way around, right? We want to actually be able to obtain continuity. So conversely, if the F preimage of every open subset of the real numbers is an open set, Okay, well now we want to show that f is continuous. Okay, well to be continuous on D, that means we need to show it's continuous at every point of D. All right, so let's take a point of D. So, and if A is some element of D, then what can I do? I apply f to A, which makes sense because A is in the domain. And now once I get into the domain, I can just say, okay, well, I have f of A, and I want to write down an f of A coin, right? So here we go. We have D, we have R, there's our function f. Here is some point A and D. I apply f, I get f of A, and now I write down an f of A coin. Okay, fine. So then for any f of A coin, okay, which of course is an open set, the f preimage, well, I'm taking the f preimage of an open subset of the real numbers, so it will be an open set. So the f preimage is even an open A set if I like, but is an open, that's fine, an open A set. Okay, so we know it's an open set, but it also contains A, right? A is certainly in the preimage of f of A. Okay, so the f preimage is an open set, but it contains A, so it's an open A set. But every open A set contains an A coin. Why? Well, what did it mean to be an open set? That means that all of your points are interior points. But to be an interior point, that means the set must contain a coin, right, for you, right? So if my point is A is an interior point if my set contains an A coin. Okay, fine. So an open A set, which contains an A coin. All right, so now my preimage of the yellow bit, right, contains some A coin. So this green section, this A coin, is all mapped into this yellow part. Okay, but if I apply f to this A coin, it maps into this f of A coin. That's exactly what we're looking for when we talk about continuity. All right, so at least once we intersect with D, but of course, right, we're working, when we take this preimage, we're only getting things in D anyway. Okay, so it contains an A coin, and thus f is continuous at A. Okay, all right, so maybe we write this down using symbology in case the words are a little too confusing here. Okay, so I have some f of A coin, right? So f of A minus epsilon, f of A plus epsilon. I take the preimage of this set, and I know that it is some open A set. Okay, so this is a subset of D. It is open because we're taking the preimage of an open set, and f is continuous, and A is contained in here. Okay, I know now that there is some A coin which is contained inside this preimage, right? Because A is contained in here. This is an open set, and every point in an open set is an interior point, which means that you're going to have some A coin contained in this open set. And so if I apply f to A minus delta of epsilon, A plus delta of epsilon, well, because it's in this preimage, that means this is contained in f of A minus epsilon, f of A plus epsilon. And this is precisely what you need to show happens for f to be continuous. Okay, so either way, we've proven the result. All right, so why did I call this a topological characterization of continuity? Well, you notice here that the right-hand side, the F preimage of every open subset is an open set, is just relying on open sets. And when you write down a topological space, the open set is the primary object. That's all you need here, right? So we didn't actually have to talk about coins or distances or anything like that. We're simply, talking about preimages of open sets. So that's the reason. Now, why specifically do we have to talk about open? Why not maybe talking about closed? Well, let's take a look at what happens when we look at the preimages of closed sets. So let's say I have, again, my F. It's going from D to R. And I can assume this is still open here. That's fine. And I'm going to take a closed set. So let me use maybe a C. Okay, so this will be a subset which will be closed. And I want to take the preimage of C. Fine. So I take the preimage of C. This is going to be all the points in D which map into this closed set. Right? So this is a closed set. Okay, now, if I want that this preimage is closed, it is enough to show that its complement is open. So let me look at the complement of this set. So what is this complement? This is equal to all the points in D such that when I apply F to X, I do not end up in C. So F of X is in C complement. Okay, but that's precisely then the preimage of C complement. Right? The preimage of C complement is all the elements of D that map into C complement. But because C is closed, that means that C complement is open. And if I take the preimage of an open set with a continuous function, right? Of course, I'm assuming here F is continuous. If I take the preimage of an open set with a continuous function, then I know that this set is open. So this tells me that the complement of the preimage of a closed set is open. And this implies then that the preimage without the complement is closed. So in fact, this result extends to closed sets. So if you have a continuous function, you take the preimage of a closed set, you will get a closed set. All right, hope this is helpful. We'll see you next time.